Hi engineers. Today we are going to discuss about Fraunhofer diffraction at a single slit. Take a laser as a light source and we will take a rectangular narrow slit, and whenever laser pass through rectangular narrow slit, it will get a diffract at the slit and we will get the light intensity pattern as shown in this figure. Right, then we will do regular procedure in order to calculate wavelength of the laser source. This is one of the applications for single slit diffraction. Now we will get into the theoretical part, how the intensity pattern will come, where we can observe light intensity at a center, it's a maximum, and whenever we move away from the center, it slowly decreases. Let us consider a slit AB, width of E. E is the width of the slit. We will consider a plane wave front is approaching to the slit. So whenever it passes through the slit, in many ways it will get diffract. But here we will take two paths, where one path is a direct falling of the lights on lens and another one is the rays which are diffracted an angle theta. Now our main motive is to calculate the intensity. So in order to get the intensity, the order we have to go is we have to get the amplitude before it. In order to get the amplitude, we have to get the phase difference. In order to get the phase difference, we have to get the path difference and secondary wave fronts. Once we will get the intensity, we will differentiate with respect to the particular parameter in order to get maxima, minima. Here we get the two solutions, that each solution will give the condition for maxima, another one give conditions for minima. That's the total story. And now in order to get the path difference for these straight waves and deviated angle theta waves, we will draw a perpendicular to the line with an angle theta. So it will form a triangle ABC with angle theta. Our idea is to calculate the BC, which is a path difference for these two waves. In order to get this BC, we will consider this triangle, and from that we will write a trigonometric relation. So let's move further. To get BC, AB is, that is nothing but a width of the slit. So sine theta, opposite side by hypotenuse. So that is BC by AB, that will give BC is equal to AB sine theta. Now the phase difference delta equal to 2 pi by lambda into path difference. We have to calculate the phase difference. So delta is equal to 2 pi by lambda into path difference. So path difference is equal to A sine theta. In order to go further, initially we thought it is single slit. Now that slit is divided into n equal parts. Each part has an amplitude of A. Then the phase difference between any two conjugative waves from n parts is 1 by nth of total phase. So total phase is 2 pi by lambda E sine theta, and 1 by n is the number of the slits we made now. It's an assumption. So this total part we will assume as a T. So from the method of vector addition of amplitudes, the resultant amplitude R is given by R is equal to A sine nd by 2 sine d by 2. Now the story is very simple. We have to substitute the d value in this expression and simplify the result. So we are left with R is equal to A sine pi e sine theta by lambda sine pi e sine theta by n lambda. This is the expression. Now we will assume this total upper part as a beta here. We can assume as a alpha also. Now the expression will become like this: sine A sine beta by n. So this denominator value we will approximate sine beta by n as beta by n. Then on simplification we will get R is equal to capital A sine beta by beta. So that Na equal to, if this is the pattern we will get for the single slit diffraction. The central one will be the maximum. Whenever we move away from it, it will go decreases. Once we know the amplitude, this is R is the amplitude. Now the intensity will be square of that one. Finally, the intensity we will get expression as I is equal to I naught sine beta by beta whole square. Now, so in order to get the maxima and minima, what we will do is we will do directly dou I by dou beta is equal to 0. From that we will get the condition. In order to get maximum and minimum intensity, we have to do dou I by dou beta is equal to 0. It means that we have to differentiate this expression with respect to beta. Once we differentiate that one, Finally, what we will get is two conditions we will get. Sine beta is equal to 0, beta is equal to tan beta. So in this, for minimum intensity, sine beta by beta will be 0. That's a sine beta is equal to 0. This is possible only plus or minus m lambda. It means that m take the values from 1 to 3 onwards, and whereas for maximum intensities we have to solve this beta is equal to tan beta. For that purpose, what we are supposed to do is we have to draw the tan beta graph. Y is equal to two graphs we have to draw. One is y is equal to tan beta, another one y is equal to beta. On solving these two, we will get beta values. These are the conditions, and when come to the applications, by using single slit diffraction, we can calculate light source wavelength, which is an experiment we will do in the laboratory. Thank you for watching.